I'm pleased to be invited to be on this panel and to describe the research that we're doing at the laboratory. I want to describe the efforts of our team in which we're using computational chemistry and physics to design and assess energetic materials. We have several goals. We want to use these capabilities to predict properties of the materials that are related to performance or sensitivity or environmental hazard, explore these on the computer before we ever invest resources in poor candidates. We want to use this as a screening tool. We also use the methodologies to identify the fundamental mechanisms that control the conversion of the energetic material to its final products. And the hopes of understanding these mechanisms, we can exploit this information to design an energetic material to behave in a specified fashion at exactly the right time that's a benefit most to the soldier. And the benefit of these methodologies and these tools for the soldier is we're going to be able to give them better energetic materials that with reduced vulnerabilities much cheaper and much more quickly. Now the methodologies that I'm going to be describing today are all based on atomistic simulation methodologies, and the ones I'm going to focus on today are quantum mechanical and classical mechanical methods. Now, I'm very pleased to say that for the almost 20 years I've been with the laboratory, they have strongly supported the development of this program of a suite of computational tools for predictive properties of energetic materials. And the program has grown significantly from other Army programs. I want to point out that RDECOM has an environmental quality technology ordnance program in which we are tasked with trying to find replacements for RDX, conventional explosive, widely in use. RDX is a neurotoxin, and it's a major contaminant of training ranges, and so there's a great need to replace this with something, an environmentally friendly alternative. We are providing the theoretical support, our design tools, in trying to find such alternatives right now. We're working jointly with Professor Tom Kropotki at the University of Munich. He and his group are actually doing the synthesis work and developing these environmentally friendly alternatives right now, and he's got two members of his team here presenting at the Army Science Conference. I hope you'll go and see the talk and the poster associated with this effort, but it's a very exciting effort to find environmentally friendly replacements of these energetics. We're also supported by the Office of Naval Research. We've been tasked by ONR to collect and assess all models and simulations associated with energetic materials research. And our goal is not only to assess them, but we're to identify deficiencies, make recommendations for changes, or fix them for use in our programs. And finally, we were recently awarded a Software Application Institute. This is joint with RDEC, in which we are to put together a suite of multi-scale simulation tools to model the response of munitions to various insults, and I'll be talking about that at the end of the talk. Okay, before I go into the technical portion of my talk, I'd like to acknowledge the many contributors to the research I'm going to be presenting here. These are the members of my team right here. All of them are theoreticians except for one. Jennifer is our lone experimentalist. She's the one who keeps us all honest. And we have numerous academic and other government agencies who interact with us. Mainly, they're mostly theoreticians because we do a lot of incorporations of their models into our programs. But we have strong ties with the small community of synthetic chemists involved in energetic materials at the DOE, and of course with the University of Munich. We provide the theoretical support, and we're quite willing to do that because they provide us with information, detailed information about the new energetic materials that they're developing, and we can use this information to further advance the models that we're developing. Okay, I'm going to be describing mainly the models that we use to explore dynamic behavior of energetic materials, and we're going to look at classical molecular dynamics and quantum molecular dynamics today. Now, these upper frames show melting of nitromethane. I've got a modeling of molecular dynamics, modeling of self-sustained detonation, reactive materials, which I'm going to talk about. These are all classical models, and a classical molecular dynamics simulation involves integrating F equal ma for each atom in a system, a very simple simulation. The The unfortunate thing about classical molecular dynamics is this requires a model description of the interaction between the atoms in the system, a model. So if you have a bad or an inappropriate or incomplete description of the interactions of the atoms in the model, your simulations are not going to be that good. They're limited by the description of the model. So it's much more advantageous and desirable to use quantum mechanics to describe the interatomic interactions because that's first principles. That's the answer. And it's only been within the past couple of years that the algorithms and the computational platforms have advanced to the point that we are now able to use, to apply quantum molecular dynamics to systems. And I've got some animations that my team has done in which we're exploring the response of shocked energetics materials, both conventional and what I'm calling disruptive, using quantum molecular dynamics. This is the response of shocked PETN, probably the largest quantum molecular dynamics simulations ever been attempted. And this is polynitrogen. I'm going to be talking about this at the end. And this interesting little thing is hypervelocity collisions of nanodiamonds, which we're exploring as potential energetic materials. And that leads into my next slide. Why are we interested in nanodiamonds as energetic materials? Well, the story starts with several years ago. We were contacted by the intelligence agencies to have us use our computational abilities to explore something called structural bond energy release. Now, structural bond energy is merely energy that is stored in a material that is in a metastable state, like a high-pressure phase of some material. And the phenomenon of structural bond energy release is not new. It was observed in 1930 by Peter Bridgman when he subjected a series of simple inorganic materials to pressure in a diamond anvil cell and then suddenly subjected them to a shear. And oftentimes these cells would explode. And it didn't receive much attention in the United States, but the former Soviet Union had an extensive SBER program. And one of the materials that they were particularly interested in was diamond. So they came to us and they said, would you start using your methodologies to explore high pressure phases of diamond that might indicate it is an SBER material? So we did. We did a bunch of quantum mechanical calculations on very high pressure phases of diamond, and we saw nothing unusual. They looked like high pressure phases of diamond. But during the course of our study, we stumbled upon a very interesting theoretical and experimental study on nanodiamonds in which the people who were studying it, they were studying it for some sort of special electro-optical property. They made a very interesting statement that they said that the nanodiamond had a structure such that the surface was fullerene-like while the core was diamond-like, and that there was tensile stress on this nanodiamond that was compressing the core. And that intrigued us because we knew that whenever diamond is compressed, you compress it just a little bit, just make the bonds a little bit small, and the pressure of the material goes up intensely. And we thought, well, this might be how they are trapping energy into diamonds, is through nanodiamonds. And so we performed a series of quantum mechanical calculations. These are series starting out with a carved out chunk of bulk diamond, and we subjected it to quantum mechanical geometry optimizations. These are steps in the optimization. This is the final optimized structure of a nanodiamond. And it does reconstruct to where the surface is fullerene-like. It's got these funny Mickey Mouse ears, we call them that. And we looked at the core, and the core is compressed to a degree that corresponds to about 50 gigapascals if it were in the bulk. That is a tremendous amount of energy in a very small space. So we came to a hypothesis that if you've got that much energy within this thing, what happens if you suddenly disrupt that shell and let that compressed core expand? We think, or we hypothesize, that it might occur so rapidly there'd be a tremendous energy release. So at this point, we decided to perform some quantum molecular dynamics simulations of something to disrupt the core, and the simplest thing we could think of was hypervelocity collisions, which you showed just a minute ago. So here are the movies, and I've got still snapshots of the process, but you can see at this hypervelocity collision, the thing just rips apart, but it doesn't reform a cluster. the whole thing just comminutes. It is doing exactly what we were expecting it to happen. The whole inside is just exploding out into space. And these are fragments, reactive fragments of carbon. You've got a few monomers of different sizes. You've got atoms. And if these reactive species are in the presence of atmospheric gases, if they hit any molecular oxygen, you're going to have spontaneous combustion. You're going to have huge energy release. And so this might be a potential energetic. We don't know if this is why the former Soviet Union was so interested, but it's certainly something that we're going to pursue. Now, this has been supported by an in-house research initiative, the Director's Research Initiative, and we don't have just a theoretical component. Again, we have our lone theoretician in our group. Jennifer is trying to figure out ways to crack the shell. She tried it in a diamond anvil cell. It didn't do it. She tried subjecting the diamond anvil to shear. It didn't do it. But she's working on some new ideas. So we hope to be able to do this. And if nothing else, we're going to do some sort of explosive launch, and we're going to collide those nanoparticles and see if we can see the event later on. Okay, the next type of simulations I want to talk about is we are now looking at reactive materials, not just conventional energetic materials, but we're looking at reactive materials, which are essentially intermetallic alloying reactions that they're considering putting in munitions so that they can deliver energy to the target. And we have a mission effort, but we're actually working with Tim Wise at the Johns Hopkins University. He is being supported by an ONR Muri on reactive materials, and he designs nanolaminates of these foils, and in particular nickel aluminum nanolaminates. He's done a lot of studies on these. And so when we started the collaboration, he said, okay, the first thing I want to understand is thermal loading. Before I go into shock loading, I want to understand thermal loading. So we set up the simulation and tried to do it. And he said, okay, do it at 1100K. We'll get started and it'll go. So we set up our standard molecular dynamics simulations with the system at 1100K. And reaction starts occurring at the interface where the alloying starts occurring. It starts mixing, and it went for a little while, and the thing died. And we couldn't figure out why, because the experiments, the thing went to completion. Well, when we started examining why this thing was dying, we looked at the temperature of the system. It was very, very hot as energy had been released, but the pressure inside the material was extremely high. It was about 12 gigapascals, and then it wouldn't go anymore because it was under such high pressure that the atoms could not mix across this interfacial region and cause the alloying reaction. And so it was real obvious, oh, pressure plays a huge role in this reaction process. So we modified our simulations in which we coupled the equations of motion, F equal ma, to a barostat. So what that means is, as you're integrating the equations of motion, the system heats up and pressure starts accumulating. It's hooked to this barostat that's going to let the box expand a little bit so that the pressure is maintained at a desired pressure. We did that. Maintained it at 1 atmosphere. The thing went like a shot. It did exactly what it was supposed to do. So we found a controlling parameter in the reactive material process. Pressure can control the reaction. So the next question is, does the reaction mechanism change? And we found that no, it didn't. We did these types of simulations for a variety of pressures, and we also saw the same thing. Now, these frames in the center are system temperatures versus simulation time, and they all show the same profile. They just show different rates. These are the same profiles at different pressures, and they either go really fast at low pressures or really long at high pressures. But they all have the same feature. You start out at a system temperature. As the reactions occur, the system starts to heat up, and then you first have this little drop in temperature. That is associated with the melting of the aluminum layer first. Next, temperature rises. There's another drop. That is absorption of the nickel layer to melt it before it finally takes off and finishes mixing. And here's an animation of the process where we watch the atomic position, and you're going to see the local temperature of the material as it goes throughout the simulation, because we want to see where the heat is going as the alloying reactions occur. And it's going to get hot. And you can see that this is getting the hottest. The heat is preferentially going into the aluminum layer. It's melting it. It's getting hotter and hotter. The heat is now flowing into the nickel layer, and it's getting ready to melt it. You can see that it finally melts, and then it just keeps heating on and on and on. Now, why this is so important to an experimentalist is before these simulations, Tim had not considered including in his continuum scale models the role of melting. he had not considered the mechanistic step of melting, and that's a key component in how this stuff works. And we've also shown that pressure influences the reaction rate. So that is a design parameter for someone who might want to tailor a reactive material. Okay, so we're transitioning these things both to experimental programs. I talked about the reactive materials program. I just want to briefly touch on polynitrogen. This was a really fun project. This was also supported under Mr. Miller's Director's Research Initiative. Polynitrogen is an extended solid, and it's kind of like the ultimate environmentally friendly energetic material because what happens is polynitrogen can exist. You can make it if you take molecular nitrogen and superheat it to thousands of degrees and compress it at huge pressures. It will transform from molecular nitrogen, which is a strong triple bond, into a singly formed polymeric form like this. And if you could stabilize that at room conditions and use that and somehow transition it where it goes back to molecular nitrogen, you have the most environmentally friendly explosive product known to man, and you have a huge energy release. So it's a highly desirable product, but unfortunately it's not stable at ambient conditions. You release the pressure and it goes back to molecular nitrogen. So Jennifer actually won a DRI award to try to stabilize polynitrogen, and William Matson, who had done his thesis work on polynitrogen, had observed that the instabilities in polynitrogen were due to defects that could be stabilized by insertion of simple things like hydrogen. He said, add some hydrogen, Jennifer, and it's going to stabilize the thing. She did. And she brought down the conversion temperature, I think, down to, she lowered the transition pressure significantly. And in fact, at one time, I think she had generated some sort of polymeric form. We're not sure what it was, but it was stable at the bench level for about 2 weeks before it turned to black goo. But anyway, this work is now being pursued under a WMRD-supported innovation proposal. Joint with Washington State to look at extended solids. They're continuing trying to find ways to stabilize polymeric nitrogen. So the work is continued. We're very, very excited about this. And I want to also state that the models that we're developing on our team are also transitioning to this new high-performance computing software applications institute. This is, as I said, a grant awarded by this agency to both RDEC and ARL to put into place a framework of multi-scale models that will allow us to model munitions response. This is a very important project because right now all munitions must be insensitive munition compliant. Anything new that is made must meet certain IM criteria. And so right now the models that are used in the munition design process are all continuum level, and they have a very high degree of empiricism that depend on extensive, time-consuming, and test and evaluation. We're trying to eliminate a lot of the test and evaluation by putting into place some subcontinuum models that will capture the salient chemistry and physics to allow us to have a robust design tool for these munitions design. And so we're getting that in place. This is the first year of the program. We're just getting it together. But right now we have some very powerful tools that we can already add to this suite. Okay, and that concludes my talk.